Welcome back to my YouTube channel. Today we're going to be talking about two reactions called the Robinson Annulation reaction and the Cannizzaro reaction. These two are somewhat interconnected with the previous reactions that we covered in the last video, which were the aldol reaction and some of its sub-reactions, such as the aldol condensation, retroaldol, aldosylation, and the Michael addition reaction. So the way I want to structure the video is I'm going to show you some of the major players, some of the reagents, intermediates, and products, or really just the intermediates right here in this card that they're going to be in the reactions. And I also want to define two things. So if you look right here, this is an aldol. This is also going to play as an intermediate in one of the reactions. It's just a carbonyl adjacent to an alcohol with one carbon separating between them. This is an alpha beta unsaturated carbonyl. It's kind of hard to see the name of it, but this weird looking A stands for alpha and the weird looking B stands for beta. And you can tell based off the name the structure of the compound just by the simple fact that carbonyl indicates they are carbonyl. The alpha beta indicates that there's an alpha carbon here and a beta carbon 2 units away. The alpha carbon is 1 unit away, the beta carbon is 2 units away. The unsaturated parts means that they are unsaturated of hydrogens, meaning they're lacking hydrogens, meaning in order to make up for the fact that they're lacking hydrogens and they need 4 total connections to 4 things, these carbon atoms, in order to be neutral, they make up for it by forming a pi bond. To tell you that there's alpha beta unsaturated carbonyl is just a fancy way of saying that you got a carbonyl and then an adjacent double bond. And then next, if you look over here, this is enolate ion. Enolate ion is a resonance structure between that of a negatively charged oxygen with an adjacent pi bond, and or a double bonded carbonyl with an adjacent negative bond, or not negative bond, negative charge. And of course, the actual, if you were to look at the actual molecule itself, it wouldn't be either or, it would be a hybrid of both of these. However, when we think about these reactions, we tend to think about, in this case, we're going to tend to think about it in terms of the one on the right. And then here we have the hydride ion. The hydride ion is just a negatively charged hydrogen. And then the two definitions I want to look at is we're going to be mentioning this idea of oxidation and reduction, as well as a disproportionate reaction. These two are related in the sense that disproportionation reaction is just where one thing is going to be oxidized while the other is simultaneously being reduced. And oxidation means loss of electrons and reduction means gain of electrons. This can happen by several means. I also made a YouTube video on that, I think. So this is the major players. First up, I want to look at the Robinson annulation reaction. The Robinson annulation reaction is interesting in the sense that we've kind of already gone over some of the stuff relating to it, which is that we've already gone over in the previous video the Michael addition reaction and the aldol reaction. And so what the Robinson annulation reaction is just a combination of those two things plus one more thing all in one major reaction. And the order of events that this takes place in is the Michael addition reaction will take first. Secondly, you will have the aldol reaction, or an intramolecular aldol reaction. And then thirdly, you have a dehydration where you lose the hydrogen to create a negatively charged carbon, and then followed by loss of an alcohol through rearrangement. So let's look at the general mechanism. Is right here at the top right corner. Top right corner, you have a cyclic compound with a ketone right here. The ketone theoretically is anywhere on this, and then this is an alpha beta unsaturated carbonyl, like we said before. And when you react these two in the presence of water, hydroxide ion, a very strong basic solution, and the presence of heat, which is what this triangle means, you'll get a bicyclic compound with a alpha beta unsaturated ketone. Bicyclic meaning you have these two cyclic compounds with 6 carbons to each that do share, and it's also fused, by the way. And as you can see, here's the double bond, here's a carbonyl specifically ketone, because it's bonded to 2 other carbons rather than 1 carbon, 1 hydrogen. And so yeah, so first we're going to do the Michael, like I said before, the Robinson annulation reaction consists of really 3 big things. That is the Michael addition, aldol, and then dehydration. First, It's the Michael reaction. So what we're going to do is that this cyclic ketone is going to act as the Michael donor, and it's going to be, by effect, the nucleophile. It is the electron-rich atom, and it's going to have a negative charge because that's how, like here, Michael donors have a negative charge adjacent to a carbonyl. And to get there, all we've got to do is we've got to react it with a base hydroxide ion to remove or deprotonate an adjacent alpha hydrogen to the ketone. And then you get a negative charge here, and this is an enolate ion. Like I said before, it exists in 2 resonance structures, but really we're only thinking about this one for the moment being. And then when you react this enolate ion with the cyclic enolate ion, you're going to react it with this alpha beta unsaturated carbonyl, and it's going to attack here at the beta carbon. If it attacked at the actual carbon here, you would give a different result, but we're thinking about it in terms of this beta carbon. And so when it attacks there, as you can see with the arrows, they're going to add to each other to produce one larger compound from this point right here, the negatively charged carbon here, to this beta carbon here. In order to do that, you have to have rearrangement of the double bond, as well as the double bond of the carbon, as well as a double bond between the carbon and the oxygen, ultimately yielding this. So as you can see, if you want to look at, like, you know, what is this really? You just have to think that this right here, the one on the left, is the one on the left in this case, and the part of the right is the part of the right here. And they just added together. The reason why the oxygen is negative is, again, because we had to rearrange the alpha, beta, unsaturated carbonyl in order to add them together. And so it's negatively charged, and there's an adjacent double bond here, which means it's an enolate. And so in order to, and I kind of drew this a little weirdly, but this arrow, the next step in this reaction isn't this, it's all the way over there. And so in order to solve the problem of this negatively charged oxygen, what we're going to do is we're going to react it with water. As you can see here, here's the H and then it's OH. And you're going to add a proton. Water is going to act as an acid in this case, and it's going to add a proton to the double bond so that you can switch everything around so that this enolate becomes a ketone. And so here, now we're here. Again, we're not down here. I kind of wrote it kind of weirdly. So now we're here. So the next step is, this is the intramolecular aldol stabilization sort of thing. So the thing is that what we're ultimately going to do is we're going to react it with a hydroxide ion base to remove a hydrogen. And there's a couple different points at which we can do this. And when we remove the hydrogen, it's going to have a negative charge, and the negative charge is going to rearrange with the carbonyl here to produce a bicyclic compound. But the problem is that there's multiple points at which we could do this, because there's multiple points of carbons with hydrogens that we can deprotonate. So really, the way that we figure out which sort of spot it's going to take place at is based off of what the resulting numbered ring it would form. So in this case, here I drew in blue. I don't know if you can tell it's blue. This is a possible hydrogen. Here you could deprotonate, and here is another possible hydrogen you can deprotonate. If you deprotonate this, you will form a 4-membered ring, because this negative charge will attack here and rearrange here. It would form a 4-membered ring. And if you did it here, it would form a 6-membered ring. And the idea is that 6-membered rings have less ring strain than 4-membered. They're more stable. And they're more stable, so it's going to form the more stable one. So it would form based off of deprotonating this hydrogen as opposed to this hydrogen. And so once you deprotonate it, there's a negative charge, and then it rearranges itself to form this bicyclic compound. If you notice here, it had to, in the process of doing so, it created a new carbon bond and removed a pi bond with the oxygen. And then the resulting structure is this bicyclic compound, where you have a carbonyl here, and you have a negatively charged oxygen here. And so after that, of course, we're going to react the negative charged oxygen with water. The water is going to act as an acid to add H. And when you add O to an H, you get an alcohol in this case. And so this next part, like I said before, it's Michael addition, aldol reaction. And then we just did the aldol, and then lastly, it is the dehydration. The dehydration is going to take place in really 2 parts. One, we're going to remove a hydrogen of an adjacent. We're going to remove the hydrogen adjacent to the carbonyl in between the alcohol and the carbonyl, and then we are going to remove the alcohol group. So like I said, water acts as an acid, makes the negatively charged oxygen an alcohol group, and after that, in the presence of heat, to cause the reaction go to the right towards the product side, and hydroxide ion, you're going to remove an adjacent hydrogen, therefore there is a negative charge, and then the negative charge will convert itself, will rearrange to a pi bond, thereby expelling the alcohol. And so again, your ultimate product would be this bicyclic compound where it's contains an alpha-beta unsaturated carbonyl, and you can tell because here's the carbonyl, or this is an unsaturated ketone, because here's the ketone and then there's the double bond right there. So that's the Robinson annulation reaction. This is a Cannizzaro reaction. I'm not sure if I'm pronouncing that right. The Cannizzaro reaction, like I said before, and this little beginning card, it's going to be a disproportionation reaction. One thing is going to be oxidized, one thing is going to be reduced. And by oxidation, of course, I mean one thing is going to lose electrons, it's going to go up an oxidation state, and one thing's reduced, it's going to go down an oxidation state. So what ultimately is going to happen is that you're going to have two aldehydes with no alpha hydrogens. Meaning, if you look at this R group cannot have any hydrogens attached to that immediate R group. Otherwise, you'll get a different you'll get the aldol reaction. And so ultimately what happens, again, these are two identical aldehydes with no alpha hydrogens, and you react in the presence of hydroxide ion and water to ultimately produce two possible compounds that kind of convert themselves into a carboxylate ion. Originally it was one of them, the thing that's going to be oxidized will be changed into a carboxylate acid, and then since there's base, it's going to lose a proton or an hydrogen, and that will become a carboxylate acid or ion as seen right here. And the other thing will be reduced to an alcohol. So how does this happen? So first we're going to look at here, and we have benzyl aldehyde. This is a benzene with an aldehyde right here. And as you can see, this carbon right here, as you see by the fact that you have one connection here, one here, and there's a double bond, there's no alpha hydrogens there. So therefore, this will undergo the Cannizzaro reaction. So the first thing is that, like I said before, this is the presence base, and base is going to actually attack and add itself to this point right here, thereby removing the pi bond to the oxygen, creating a negatively charged oxygen to make room for it. And then you'll get this. So it's a negatively charged oxygen, alcohol here, benzene here, and then hydrogen here because it's the aldehyde. And then you're going to react what you get from this first step with a parent molecule. And by parent molecule, I mean basically another one of the original molecule unaffected. So these two, this and this, are the same thing, and this is what you get after deprotonating this. If that makes sense. And then I kind of drew it kind of weirdly, but the next step is downwards. It's not to the right because there's not enough room. This next area it's down here. So what's going to happen is that this is ultimately the thing that's going to be oxidized, this whole column on the left here. And then this whole column on the right is the one that's going to be reduced to an alcohol. And so what's going to happen is first, I kind of drew it kind of ugly, I'm sorry. Or excuse me, so yeah, so this occurs first through a hydride ion shift. That is, in order to form a double bond here for the oxygen, the negatively charged oxygen, you're going to remove the hydrogen, and it's going to attack here at this point of the parent molecule, thereby creating a negatively charged oxygen. Yeah, so, and then after that, this negatively charged oxygen here, it's going to be protonated by water. Water's going to act as an acid to produce an alcohol. And then, so that was just this step, this step, this step on the right side. And the left side, if you look, by removing this hydride ion and getting a negatively charged hydrogen, you have room to form a double pi bond with the oxygen. And then, yeah, and then this is the alcohol from the hydrogen, or the hydroxide ion right here. And so essentially what you get is a carboxylate acid, but the problem is that this is in a basic solution, so theoretically that carboxylate acid is your product, but because it's in a basic solution, it is going to be deprotonated by one of the hydroxide ions, either reformed through somewhere in the reaction or just it was there originally. And so what's going to happen is that hydroxide ion is going to remove a proton of the alcohol and ultimately give you the carboxylate ion. And so again, the way that this works is that you have two aldehydes. In this case, the aldehyde is attached to benzene in order that it would fulfill the requirement of the Cannizzaro reaction of having no alpha hydrogens, meaning here at this R group, it cannot have alpha hydrogens because it's benzene. There's no room for alpha hydrogens, as seen by the fact if you just look at this carbon and you count how many things it's attached to. In this case, it's 1, 2, 3, and the double bond is 4. So since it's 4, there's no room for hydrogens, and there's no hydrogens. Therefore, you have 2 of these. One of them will be deprotonated and then reacts with its parent molecule, and then they undergo oxidation and reduction to form either the alcohol or the benzoic or this carboxylate ion. So yeah, I think that's it.